So these iron fertilization experiments, they were started when this became a big issue. What controls phytoplankton production in nutrient-rich areas of the ocean? And these areas are called high nutrient, low chlorophyll regions, HNLC, because the nutrients are always there at the surface, but in surface water, but chlorophyll is low. That means that the productivity is low. Those nutrients are not being utilized. Now, we know from our past experience, people have been doing the studies of the ocean in coastal waters, and in coastal waters, you never have that. In coastal waters, if you have high nutrients, it's only temporary, because then sooner or later, the phytoplankton, not sooner than later, the phytoplankton start growing, they take up those nutrients, and then you get high chlorophyll. And that's when the seasonal cycle continues, right? But in these places, in the open ocean, it was a paradox that you always had high nutrients and the phytoplankton didn't use those nutrients. The question was, what controls phytoplankton production in nutrient-rich areas of the open sea? And the nutrient-rich areas are here, the subarctic Pacific, the equatorial upwelling, and the Southern Ocean. So this is a diagram which I'll show later on. So the explanations were deep mixed layers that the phytoplankton were light limited. This applies to the Southern Ocean. Southern Ocean, you have deep mixing, so you could assume that the phytoplankton just are not able to use the light, the nutrients, because there's not enough light. And that was the explanation that I favored, because I had only worked in the Southern Ocean up to that time. And the mixed layers were like 100 meters deep, also in the summer, but we didn't get this higher production. And then there was the issue was iron availability, that iron is limiting. And most biologists at that time didn't believe that, because you couldn't think that iron, why should iron, just one element, have such a control on the ocean ecosystems? And the other explanation, and this came from the subarctic Pacific, heavy grazing pressure by zooplankton. So those were the three possibilities that were discussed at the time. And the interesting thing is, or what sheds light on people's thinking, is that people who had only worked in the Southern Ocean, they favored the top one. And people who had worked in the subarctic Pacific, they favored this one. And in the equatorial Pacific, there you have a lot of light, the mixed layers are shallow, and you don't have that kind of zooplankton. So it was just, we couldn't reach an agreement. And it took a long time to understand that it was iron availability, and it was only iron availability. That was the only reason. So here you see again the same region, the subarctic Pacific, the equatorial Pacific, and here. Now, the North Atlantic behaved much like coastal systems. There was a spring bloom in the North Atlantic. And the North Atlantic spring bloom was taken as the example for plankton ecosystems in general, right? So the North Atlantic was considered the rule because we always had that in coastal ecosystems, that same situation, and the others were the exception. But it turns out it was the other way around. The North Atlantic is the exception. But that only happened in the 90s, that we got that far. The North Atlantic is an exception because it gets dust from the Sahara. The Sahara is a huge reservoir of dust, and dust contains iron, and that's why there's a bloom there. Now, this has a lot of repercussions, because this is something which you all should know. For the exams, I keep saying that. What is important? There are three large high nutrient, low chlorophyll regions. The subarctic Pacific, I've said already that there's now overwhelming evidence that phytoplankton growth rates here are limited by the availability of iron. It's only iron. It follows that the rest of the ocean received an adequate iron supply. Where you have high chlorophyll concentrations, or you have a high productivity, there's a lot of biomass, it means there's iron. Now, the iron hypothesis was started by John Martin. Here, this is John Martin. He was a biologist who became a biogeochemist from Moss Landing. And he and his group, they developed techniques to measure iron or to prove that iron was actually at extremely low concentrations because of the contamination problem. So they developed so-called ultra-clean techniques to be able to measure iron at very low concentrations, right? So that iron is a crucial element and that it might be limiting was around for a long time. There were also other scientists well before Martin who had that feeling that iron was a key element controlling productivity in aquatic systems in general, but they couldn't prove it because whenever they took a measurement or a sample, it was contaminated with iron. So there was iron everywhere. If you incubated a sample of water, then you always got growth of plankton. Even if you tried to keep it clean, even if you took necessary precautions, you still got big blooms, right? So when we were in the Antarctic in the 80s, for instance, early 80s, we had these tanks where we would put seawater, we washed the tanks, and then we would study the seawater in the tanks, and we got huge blooms in the tanks. So we thought that, yeah, iron, we didn't add any iron, of course, but the iron that was there naturally by itself as a contaminant was enough to make these big blooms. So that's why I didn't believe in the iron hypothesis when it came around, because I couldn't imagine the low concentrations of iron necessary to start to give rise to these blooms, right? So when John Martin came and said that iron is the reason why we don't have these, why the productivity is so low, a lot of people didn't believe him, and myself also. No, he said, no, it's not possible. So what John Martin actually proved by taking this ultra-clean precautions, by developing these ultra-clean methods, he proved that if you wash your reagents and you wash the bottles, the culture bottles and the sampling equipment and so on, very painstaking and with extreme precaution, then you could actually show extremely low concentrations of iron. And he also did cultures of seawater where the plankton didn't grow, right? So it was the control, his controls actually proved that iron was limiting. Now, this is in the late 80s, and when this happened, and he did about 3 experiments, 3 bottles in the Antarctic, where they took this samples, seawater samples with extreme precaution, and where they could show that the iron concentrations were below around 0.1 nanometer, nanomole. And remember that phosphate is at 1 micromole, right? Or 0.1 micromole. That means 1,000 times higher concentrations. It was just a handful of samples that he had, and he published these results in Nature. And yeah, that led to big controversy. So to solve that problem, he suggested carrying out iron fertilization experiments in the ocean. And when this suggestion came, I thought it's crazy, because if you add iron to the ocean, it'll just get lost, I thought. It'll just get mixed up and it's gone. I belong to a large majority of biological oceanographers who didn't accept this iron hypothesis. So he postulated the iron hypothesis. And what he was saying is that iron concentrations in coastal waters are above 1 nanomole. Now he measured that and showed that, but below 0.1 in open ocean surface water. And that in deep water, they are 0.5 nanomoles. In the deep water that where you have high phosphate and nitrate and so on, there you have only 0.5 nanomole. And it suffices only for a limited uptake of macronutrients. Hence, HNLC conditions despite upwelling. So even though you have upwelling of water from the depth, with very lots of nitrate and phosphate, the iron is just sufficient for a few cell divisions. And then it's stopped because it becomes iron limiting. So the plankton is basically iron limited. And iron is is also recycled by heterotrophs, analogous to N and P. However, loss rates, efficiency of regeneration to deep water are unknown. That iron that is being recycled is also quickly lost. Right? Yeah. Okay, we continue. The main source of new iron to the open ocean is aeolian, airborne, dust. And the North Atlantic is clearly supplied by African dust because of the size of the source of dust in the Sahara. Now you also have deserts off Chile and so on. For the South Pacific, for instance, or California, Mexico, for the North Pacific, but they're just not big enough. Or from China in the North Pacific, it's just not big enough to have an effect on, for instance, the subarctic Pacific or the equatorial upwelling. So he postulated this iron fertilization experiments, and most of us laughed, thought it wouldn't work. But then John Martin got the permission, and he got funding to carry out the first experiment in the equatorial Pacific. It was called RNX. And we were all watching. And then what they could show is that there was an effect. They added iron, but the equatorial Pacific is a region of very strong currents. So that patch of water that was fertilized with the iron was very quickly transported away. But then, of course, the other thing was that how do you follow the iron water, the water enriched with iron? And at that time, there was a technique developed, and it was a molecule called SF6, which is sulfur hexafluoride, SF6. And that you can measure in very small, in trace quantities, very low concentrations. So this SF6 was a tracer because the iron was very quickly gone, whereas SF6 is neutral. It's one of those gases that burn up the ozone in the atmosphere. But you need just a very small amount of it to measure it. Now, I showed you yesterday the CFCs, that we can measure the CFCs in the deep water. And those concentrations are vanishingly small, but we can still measure them because we have these techniques to do that. So this SF6, this is a scientist called Andrew Watson from England. And he had this SF6 technique under control, so to speak. So he joined on this cruise. So he measured SF6 in the water. And SF6 was added to the iron solution that was put into the ocean. And then they could measure where there was SF6. They also measured there was more chlorophyll because the iron was gone, taken up. Right? So you couldn't use the iron as a tracer, but you could use SF6. And that SF6 was absolutely essential to prove the iron hypothesis. So what was the iron hypothesis? So now we know that the bulk of the ocean is iron limited. And the in situ iron fertilization experiments have demonstrated the role of iron in driving oceanic production. Now, this is away from the coast because the coasts have a lot of iron. All the rocks, everything contains iron. So any seawater that comes into contact with sediments or with coastlines picks up iron. And then, but that iron is used up, but it's very poorly recycled. That's the problem. No? That iron gets taken out very quickly. So the iron hypothesis of John Martin, that I showed you those ups and downs of the glacial-interglacial CO2 cycles, right? And when those data came out in the late 80s, it also came out that there was more dust during the glacials. So when CO2 levels were low, there was also more dust. I'll show you some more diagrams. And John Martin said, he postulated that it was the iron in the dust that brought the CO2 concentrations down by increasing the productivity of these HNLC areas. So he postulated that it was the HNLC areas of the ocean that were taking up the CO2. No? So higher glacial dust input increased production and activated the biological pump, particularly in the Southern Ocean, accounting for the 180 ppm V is for volume. CO2 concentrations. And glacial thermohaline circulation differed from that of today. The ocean's outcast CO2 when circulation changed. The earth warmed, rainfall increased, dust supply decreased in a feedback process whereby cause and effect are not really known. What started them and what stopped them is not really known, but what maintained the glacial period or the interglacial is known, or was postulated by him. Sorry, this is a It's a okay, I should have taken this out. This is an older one. The hypothesis is currently under intense discussion in light of its potential as a means to reduce anthropogenic CO2. It's one of those, it became one of the first methods to be called, to be put into this thing of geoengineering, which we will discuss on Friday. Right? Yes? High nutrient, low chlorophyll. It was in the first slide. No? So that you should all know. HNLC is a acronym that you should all know it. Yes? That's a good question. In freshwater, you can have iron for limitation, but very large freshwater bodies. Because if the water body is shallow or has contact with the coast, then of course there's an abundance of iron. For instance, the North Sea is probably not iron limited. For instance, the North Sea. But a lake like Lake Constance could be. But I don't think there's any. Lake Baikal would definitely be iron limited in the middle, right? But not along the coast. So the coast is always iron replete. So it's only important for open ocean or open waters far away from shores. So this is what started the iron hypothesis. No, this I told you already. This is the CO2 and the temperature of these ice cores that were published in 1999. And when that came out, then 99? 89. I'm sorry, I have to check. This is wrong. It was in 89 because the iron hypothesis was published in 91. So yeah, that's a mistake. I'll have to change that. Yeah, so it came out in 1989, and there were these ups and downs in temperature and CO2, and at the same time, this here at the top is the dust in the same ice cores, in the same layers. And when the temperature was down, the CO2 was down, there was more dust. And it was a very close connection between the two. You see that better over here. This is then this is 99. Yeah, this is a longer ice core. It was, yeah, so the first one is 89, and this is 10 years later. And here the Alfred Wegener Institute was also involved. This is from another place. Another ice core was taken in the Antarctic. It was deeper, it was older, and it went back to much longer. And here we had the same ups and downs. They followed that very closely. And yeah, this went back 660,000 years. And this was published in 2005. You can see all the dates. But the point here is that, yeah, these are from different ice cores, the different colors. And you see this close congruence between iron input. So this is the iron, this is the dust input, and this is the CO2. And there's a very close congruence. Now, of course, you could also argue the other way around. You could see that in the glacials, it was drier, so there was more dust. So it's a parallelism. It's not a cause and effect, right? So that is something which also has to be considered here. Now that what we can conclude definitely is that when the land was brown, meaning when there was more dust, when it was drier, the oceans were green. And when the land is green, the oceans are blue. Right? But what is the connection? What is the cause and effect? Yeah. Now the human factor, and of course this is from 2009. Now we are far above that. But you see again here, the high dust input is related to the low CO2. Very clear. And this is just a more detailed synthesis of the relation between biological carbon pump and glacial-interglacial. And here you see a more detailed comparison of dust input and the CO2 concentration in the air. So then John Martin, there were these intense discussions, and there were conferences which I also attended where I did not agree with this iron hypothesis. But then the first experiment was carried out, as I mentioned, and it showed that they got a chlorophyll bloom. And then but there was a bit of bad luck in the first experiment because they had a heavy rainfall close to the experimental site, and then a layer of lower salinity water due to the rainfall that spread out on the top and covered flowed over the iron fertilized water, and it went down. It was subducted by the surface layer that was formed by the rainfall. So that was not clear. But then a subsequent iron fertilization experiment was carried out 2 years later, and there it was like magic. I mean, it was the people who were on that cruise, it was just a couple of weeks, it was in the tropics. They were stunned by what happened when they added the iron. First of all, they got a huge bloom in the equatorial Pacific. Now, this was RNX2. Huge bloom. But not only that, also birds were attracted, fish were attracted, life really picked up. And they were so shocked. There was one colleague of mine who said that they were so stunned that they thought that they had the kind of magical control now of the ocean. You add iron and you get this. And oh my God, can we handle this? This is the magician's apprentice, where you suddenly have a power over something. And it's so simple because you just have to add iron and then these things happen. So it was like a bit shocked. Yes? You get almost an instantaneous response. Of course, you don't see I'll show you. You don't see the chlorophyll building up because they take a couple of days to divide. So that takes, but the phytoplankton react instantaneously. John Martin was so confident about his hypothesis that he made this statement. Ocean iron fertilization was ridiculed by the media. This is a cartoon from a newspaper. Because he said, give me half a tanker of iron and I'll give you an ice age. Because he was convinced it was iron that was driving the whole thing. And at that time also there was this cold fusion had come up. Cold fusion, and that was also ridiculed because it didn't work out. But it was a claim. It was put in the same pot, iron fertilization and cold fusion. These are wild claims of scientists, and then they made fun of it. And this statement that he made at a conference when it was a joke. He just said, give me half a tanker of iron and I'll give you an ice age. That has become a kind of a meme now, which is you find all over the place, right? Now, how important is this? Oh, by the way, what I must also mention is that John Martin passed away before the first iron fertilization experiment. He fought for it. He got the funding, and he got the funding because there was one person at the National Science Foundation who believed him and said, yes, we should fund this experiment. Just one ship with a bunch of scientists. And otherwise it wouldn't have happened because we were all opposed. So you see how slender this thing is, right? I showed you this diagram yesterday, and it just shows, again, I repeat, that this is this upwelling of this circumpolar deep water, and that's fed by the North Atlantic, but also from other deep oceans, right? Also from the Pacific a bit. And this water upwells around the Antarctic continent, right? And there's also an east wind drift. This is a coastal current that goes around Antarctica in the other direction. And this is going to the east. It's the westerly winds, the winds coming from the west, push the water to the east, and it circles around the continent several times before it goes into the intermediate Antarctic water, subducts. Okay? Now, in this period, this water does not lose its nutrients because there's no iron, right? Now, if you were to add iron to this water before it subducts, then you would be having diatom blooms that would sink out and take a lot of iron, take a lot of carbon down with them, right? But then, of course, you would also be taking nutrients out. That means there would be less nutrients going into the Antarctic intermediate water. Yeah? And remember, the Antarctic bottom water is found here, but it's a small amount on an annual basis. It's not much, but it fills the deep ocean. But that's a different story because that's all ice covered and so on. So that doesn't have an effect on the productivity. But this water, this open water, the water that is seasonally covered with sea ice, and then the water belt north of it, which is not, these areas would be then productive. Huh? Oh, did I mention that John Martin passed away? But that was one of my deep regrets that I had, was that I couldn't tell him that he was right after the second experiment was carried out. Actually, after the first already, I was shocked, and I said, yes, he's right. So then I became a defender of the iron hypothesis, because you get facts and then you have to change your opinion. And then, of course, it was a relief, because then suddenly everything made sense. It fitted. No? Why HNLC areas as different as the Southern Ocean, the Equatorial Pacific, and the Subarctic Pacific, these are completely different oceans in the hydrography, everything, temperature, mixed layer depth, zooplankton population, everything. They're completely different. But they were all similar, that they had nutrients at the surface that were not taken up. And they all had in common that they didn't get iron, right? So you add iron, and that happens. And it didn't work in the Atlantic because of the Sahara. So the equatorial upwelling in the Atlantic has enough iron to also fuel the sargassum blooms that are growing there now, and the diatom spring bloom. Yeah. So this is the Antarctic and the Arctic, and that the chlorophyll distribution around Antarctica, that there's a lot of chlorophyll here in connection with the peninsula and South Georgia. That's the island of South Georgia. And that's because the currents go this way, and they go again in the other direction around South Georgia. And so this iron from South Georgia makes this bloom. And this is a standard bloom. It's there every year. And it's fueled by contact with South Georgia. Whereas this bloom is from contact with the peninsula and the islands, the South Scotia Islands around the peninsula. And then you have patches of chlorophyll here and there also. And then here also, always around the coast, you have higher iron concentrations. And this is probably due to dust from Australia and from Australia primarily here. Settling dust, right? So this is what the distribution of chlorophyll looks like. And in the Arctic, on the contrary, because the Arctic has all this land around it, you have all the nutrients are taken out very quickly. It's slightly more complicated because you have lower nutrient concentrations in the Atlantic to start with, because of the AMOC, the overturning circulation. So there's less nutrients coming into the Arctic, but it still has this iron situation. So you cannot draw conclusions on the iron hypothesis from the Arctic, but from the Antarctic, yes, because there you had this huge reservoir of nutrients.